nanohub.org.
Online simulation, and more for nanotechnology.
Thank you everyone for joining us today for our webinar, a Condensed Matter Physics class and a course-based undergraduate research experience with the MIT Atomic-Scale Modeling Toolkit. Today we have our presenter, Dr. David Strubbe. He is an assistant professor of physics at the University of California, Merced, and has been using and developing in NanoHub since 2008. With that being said, I'll hand it over to you, Dr. Strubbe.
Great, so welcome everybody. I'm very pleased to be presenting this morning. We've been a big fan of NanoHub since I first learned about it. I'm actually wearing my NanoHub t-shirt here, which I think I got in 2010 or something when I was a grad student through accumulated points from having made tool contributions and answered questions. And I try to tell everybody about the cool things we can do with NanoHub whenever I can. So I'm really glad to present about this today, and I'm glad that all of you are joining us to learn about all the exciting things we can do with NanoHub for education and research. So I'd like to get started. I'll just tell you a bit about where I'm coming from. So I'm at UCMERCED. We're very new, so you may or may not have heard of us. We're located in the middle of California, and we were founded just in 2005 as the 10th campus of the UC system. And they like to say that we're the first U.S. research university of the 21st century. We're in a little small city, about 80,000 people. We've been expanding our campus a lot. So actually in the lower right here, that's the building I'm sitting in right now, which we got done just in 2020, doubling the size of our campus as we're growing both our undergraduate and graduate student populations. And we're about 9,000 undergrads. And something I'll talk a little bit about more later is just over half of our students are of Hispanic or Latinx background, and 75% are first generation students. And we're the Bobcats. But we're a bit about where I'm coming from in terms of research. So I like to call my group the Strubbe Ab Initio Laboratory, or SAIL. And some of the things they're connected to what I'll be showing you here is related to 2D materials. So we've been doing some studies about Raman spectroscopy of molybdenum sulfide with nickel or rhenium dopants in there. Actually, this lower paper actually was just published today in Nanotechnology. I just put in the citation info here. We've also been looking at friction and sliding in doped 2D materials. And looking at how you could use dopants to make new kind of structures within within 2D materials like molybdenum disulfide, and some interesting and unusual properties that come out of them. And we're also working on developing methods that we can use to calculate the spin states in defects with an approach we call the spin flip beta salpeter equation. So some of the things we're thinking of on the research side. Today we're going to focus on this MIT Atomic-Scale Modeling Toolkit. I'm going to tell you a little bit about just the tool and its history. It's an interesting discrepancy between the name we see, MIT Atomic Scale, and actually the URL, which says UCB Comp Nano. And this is because it actually started as a computational nanoscience class at UC Berkeley in 2008. And so this was done by Elif Ertekin, who was a grad student at the time, now is a professor at Urbana-Champaign, and Jeff Grossman, who now is a professor at MIT. So I took that class in 2008, actually. Then I was the TA for it in 2009 and did a lot of work on further developing the tool to enable different things we wanted to do for the class. Then when Jeff went to MIT, this tool was used instead for an introduction to modeling and simulation class there, which he taught along with Professor Marcus Buehler. So then it was rebranded to this MIT Atomic-Scale Modeling Toolkit. Since 2016, when I started at UC Merced, I've basically been the main person developing it. And I've been using this for both undergraduate and graduate condensed matter physics classes here. And I like to say that I think we have a design philosophy here that we're really trying to manage the complexity of the underlying code that we're dealing with. So to try to enable that you can take some pretty complicated research grade codes, like, for example, quantum espresso, and rather than having to try to understand which out of 1,000 keywords you're supposed to use, to just have kind of a few that are the key things that you want to do to try to help you figure out how to do some straightforward things, and to kind of have, I would say, sort of less is more in terms of what you are able to do in the code. We've tried to avoid having just kind of a proliferation of all sorts of different options, which now are something the student has to worry about. Do I need to set these options, or what do they all mean? It's called the toolkit because there are a number of different things you can do within it, several different things in there. So some of these I'll talk about. The other ones are, some other interesting things, but that we won't get into today. So we can do a variety of different kinds of theories and things in there. I think this was a little bit tongue-in-cheek, but one of the student reviews you can find up there that I think is from the 2008 or 2009 time of the class, a student called this a technological and pedagogical tour de force. I hope to convince you that that is true. Most recently, I've been using this for a class on condensed matter physics. This is an introductory class, so some students may have learned something before, but it's not required on the subject. It's been taught for around 20 students, and this is a class that is cross-listed as being for undergraduate physics majors, also for PhD students in physics, and PhD students in the Materials and Biomaterials Science and Engineering program, or MBSE. And we work through a number of topics in this class, like the Drude model and free electron model, bonding, phonons, crystal structure, X-ray diffraction, the nearly free electron model, Bloch's theorem, and band structure, carrier statistics, semiconductor devices, and magnetism in materials. And so I guess this was the third time that I was teaching the class, I've been developing new kind of exercises and trying to fine tune what we've been doing. And so we really did, this time we had some kind of hands-on activities with NanoHub in every discussion section. So the students work in groups maybe 3 or 4 students per group, depending on how many people show up for a discussion. And then additionally, we had a few homework problems that were using NanoHub, which are related to the cure that I'll talk about a bit later. So this is a list of just the different things that we did in discussion. The ones in bold are ones that I'll show you examples of after this brief presentation to introduce things. And these were integrated to be connected to the topics that we had looked at in the previous week, basically, in lecture. So we looked at atomic energy levels and wave functions, different kinds of bonding, radial distribution functions, and solids versus liquids. Then there was, we worked on vibrations in 1D chains, a lot of visualization of crystal structure. So we actually mostly did not do this in NanoHub, but it was towards the end of the semester we implemented that you could do it in NanoHub. It's also not too hard to just do, this is not like a calculation, but just a visualization. So students can also install XCrystal or similar codes on their own laptop to do this. But NanoHub is a nice approach because it's something that everybody can definitely deal with and don't have to run into some kind of weird issues about installation. Later on, we looked at vibrations in solids, Brillouin zone paths, electronic band structures in 2D materials. And then we actually didn't really get to number 12, just some constraints of time, but it's something I've done previously. You can use the Monte Carlo Ising model tool in this toolkit to look at paramagnetism, ferromagnetism, and antiferromagnetism, which can be nice for talking about magnetism in materials. And so something that I did for the first time in the class this year, which I'm excited to tell you about, was doing a course-based undergraduate research experience, or CURE. So this is a scheme. It's been around for kind of a while in different contexts, in which we try to bring the excitement of research into the classroom. This could be like that it's the whole like the whole of a class is this research experience. That is one model that's used, or it could just be a portion of a class, which is what I've been doing here. And some of the key aspects of this are that students are learning about research methods and using them, that they're having some input into the project at hand, they're generating new research data, and they're analyzing it to draw conclusions that are not known beforehand. I mean, this last one is one of the most key. So this is the difference from the kind of traditional sorts of labs in which you might say, you know, your job is to confirm that Newton's law works or something for intro physics. Well, we already know that Newton's law works. You're doing the same lab that students did last year, and honestly, for like 200 years, people have been doing these kind of labs. And obviously those can have their value too, but this is the idea. We actually have a research question that students are working on, and I don't know what the answer is going to be beforehand. I have some idea of what things might be right or wrong, but we're going to actually, as a class, try to figure out something new. So that's an idea that students find quite exciting and engaging. And there have been a number of studies on cures showing that they improve learning and motivation for students, promote independent thinking, and increase retention of students in the major and in STEM generally. Students have the opportunity to apply their knowledge and get a taste of research, feel like they are a real scientist as they're doing science, and have a sense of belonging within the disciplinary community, and also go on to doing other research projects. So this can be sort of like a way of getting students into longer summer research projects, for example. And studies have shown also that these kind of benefits are particularly important for minoritized or underrepresented students. So that connects to what I was mentioning about the student population at UCMERCED. So these can really be good to help kind of bring everybody in and say, you're here, you're doing research, you are a scientist, you can be part of this community, you belong here in what we're doing. And so these are two helpful references I put at the bottom here that kind of summarize a lot of literature about cures and talk about some practical things about how you can run them. And so the cures I think, were started originally in biology. I think the name is sort of a bit of a joke there, that they did things like some kind of large screening. You could say, like, do any of these a few hundred molecules help to kill some kind of virus or bacterium or something like that? So every student can follow a particular protocol and see whether it does or not. So you're trying to find a cure. And so when I first heard about this, I started thinking about, is there a way we can use this in condensed matter physics or materials science? What I came up with was something related to 2D materials. So I'll just tell you a little bit about the science here for a moment, because this is part of doing a cure. If we're going to ask a research question, it has to be grounded in something that we care about the answer to in research. And also, this is something that I did in class. I used this slide and another one to try to explain to students the point of what we were doing. So a topic that people are very enthusiastic about right now in condensed matter and materials is 2D materials. So we have these materials that are just basically a single atomic sheet or a couple of atomic sheets together. They have strong covalent bonds in plane, like bulk solids, but between the sheets, they just have weak van der Waals interactions, and that helps to give them some really interesting properties, electronic and optical. We can have any number of layers from one to a huge number. You can combine them together to make heterojunctions. We can have some interesting applications for quantum computing or quantum information. And there's also some really interesting topological effects that can occur in some of these materials. And a variety of different sorts of 2D materials that can come up here. We're going to focus on transition metal dichalcogenides, the one that's in the upper left, but there's also a lot of interesting ones in this category. And of course, graphene is the original one, which is in this picture, and which Novoselov and Geim won the Nobel Prize for. One of the techniques that is really useful for probing 2D materials, like with other materials too, is Raman spectroscopy, and something you can do experimentally, and it's also relatively straightforward to simulate that. And so this is some calculated data done by my recently graduated PhD student Enrique Guerrero for just Pristine MOS2. So what I came up with as a cure for what we were going to do is we're going to look at alloys of between MOS2 and MOSE2. Actually, there's a typo that I'll fix in these slides. This is supposed to be an X here. So this is something where we just can have a range of compositions of how much sulfur is there versus how much selenium. And this is inspired by this idea of sort of the screening technique from the biologists, that we're going to find some space of structures where we can do more or less the same workflow on all of them, so that we can prescribe to the students what that workflow is, give them each a little piece to do, and then try to put it all together to come up with something that means more than any of the individual ones. So the way this worked is that was a final project for my class involving a presentation and a paper. I did a lecture on the unique physics and applications of 2D materials to give them some context of what we were talking about. And then everybody was assigned a particular structure for this material with a different concentration. I'll talk more about that in a moment. I did 2 homework assignments. So in the first one, they worked on just Pristine MOS2 and MOSE2. So this was a way of, kind of making sure we're all on the same page. This was something we all did the same thing, so they can compare notes with each other. I can provide a solution, and they can check that they understand how to do this correctly. And then they did a very first part in a next homework assignment with their assigned structure of finding the relaxed structure. And then they went further for the final presentation. They talked about this relaxation. They also chose their own property to calculate, such as density of states or elastic tensor. This was something that was not necessarily going to amount to useful data ultimately, because they all did something different, and also because they were all doing a different approach. It was harder. So they may or may not have done that correctly, but this gave them an opportunity to explore something through there. But then for all of the things that they had done systematically, where we could be reasonably confident that they did it right, they submitted all this data to a class repository in a spreadsheet, and also with all various kind of input and output files stored, so we know the provenance of this data. And then in a final paper, they analyzed this full class data set, where we've basically enumerated the different structures for alloys, and we can do things like, for example, find what the most stable structure is in here, and identify trends. And this was all done with the Quantum Espresso tool in NanoHub. So this is great. I think this would not have been possible without NanoHub, in that a few of the students had the knowledge to log into a cluster on campus, understand how to submit jobs on the cluster, understand how to work with input and output files and things like that. But most of the students didn't, and it would have just been too high a barrier for them to do that. So so we were doing this with NanoHub. So as we'll see in some examples, this was something we could kind of work through with just focusing on kind of the key physics of what's going in and out, without needing to worry so much about some of these computational details. And I'll mention we also have a parallel run functionality. So, to try to do something that's not just a demo or a homework problem, do something that's actually can ultimately be publishable, we need to do some bigger calculations, since we actually use the parallel run functionality that we added in Quantum Espresso. Great. So I see a couple of questions coming in. So I just have a few more slides. So I'll finish with that. Then we'll go to some questions, and then I'll do we'll look at some hands-on things. So this is an example of how I enumerated the structures. So basically we're talking about just which sulfur was turned into selenium. And I enumerated all of these, taking into account which possibilities could be related by symmetry. I gave students as a challenge if they could show that any of the two that I listed are actually the same, or that I missed something, then they would get a bonus. I'm not sure that they really seriously tried that, but at any rate, nobody found any hole in what I had done. So for example, the structure that I've shown here, you could flip this one upside down, for example, and that's essentially the same structure. So there's no purpose in having somebody else calculate it. Then here's some results from one of the student papers here. So showing the whole data set. So it's an example of what we can get ultimately. So here's a lattice constant versus a concentration. So 0 is MOS2 and 1 is MOSE2. And so, as we might imagine from some simple models, there's kind of a linear relationship, but it can vary a little bit from some of the structures that have the same concentration. Here we have the average bond lengths, and this is something that's important. These students are doing this for the first time. It's a class project. They're not experts. They don't necessarily have a huge amount of time to check and recheck everything as we might in research. So there's always going to be some anomalies. So we want to make sure that we're able to detect those. It's also a nice exercise for the students in looking at the data set to see, hey, something is off. And so the anomaly is a couple of people just mislabeled what was MOS bonds versus MOSE bonds. So it's actually relatively straightforward to fix in the data set. And then finally, in the upper right here, I actually have some Raman spectra. So we're comparing this one in kind of orange or darker orange is MOS2. This is in the lighter orange, that's an alloy, and in blue, that's the MOSE2. So we can see what happens in these different cases. So these are the online resources that we also put in the chat, so you can get these slides, and you can also get the webinar exercises for what I'm about to show you hands-on. And then I also want to just make a few acknowledgments. So thanks to the students in my class for bearing with some technical problems that we had and then fixed about this tool and being part of this kind of experiment. Enrique did a lot of the tool development here. Some good discussions with a biology colleague of mine named Marcos Garcia Ojeda about cures. And some of the original ideas from this actually came from talking to Dr. Anubhav Jain, who's at Lawrence Berkeley Lab. Of course, support from NanoHub was important, and specifically this cure aspect is part of a project funded by a Cottrell Scholar Award from the Research Corporation for Science Advancement. Okay, so let's talk about a few questions here, and then we can go to doing hands-on things. So
we also do have Dr. Guerrero in the chat helping answer some of the questions. So you might have a little more to say on these. The first one was, can we predict Raman spectra from DFT-based tools?
So the answer is yes, absolutely. I mean, there are a couple of different ways to do it. I think the most standard one in the literature, which is what we have implemented in the Quantum Espresso tool, is to use density functional perturbation theory. So our tool is, I think, the only one, at least that I've seen, that does density functional perturbation theory on NanoHub. So we can do phonon calculations from that, and we can get Raman spectra. So that's the source of the data I showed you. And I'll these kind of take a little while, so I won't actually set up this run for you, but I'll show you some of the outputs that we can get from that, and you can try that in your own time if you have 30 minutes. Maybe to wait for the calculation to run.
Great, thanks. And I think we had one more question that came in. That barrier of Unix/cluster knowledge has been a real issue for students here at AFIT as well. So this would help. Maybe that's more of a comment than a question.
Yep. Yeah, I totally agree. So I think that it's useful to kind of distinguish. There are various things that we might want students to know that make sense to do at different times. So on the one hand, we can use simulations to just kind of illustrate some course concepts, and that's what my main goal was here. You can also have as a goal that students can understand something about how the simulations work, like what is density functional theory, how do we do some of the kind of numerical things. That was part of the original concept of the UC Berkeley computational nanoscience, but something that I think there wasn't time to get into within what I was doing here. So I actually tried to minimize that as much as possible and just focus on the kind of general condensed matter physics. And then, of course, students can also learn about how should they really do the calculations, like Linux and clusters and compiling codes and things like that. And so, that has its place too, but a lot of students, they maybe don't really need to know about that. For example, the experimental students getting an idea of what are band structures is much more important for them than to know how you should actually do that. So I tried to split these up, and you can focus on which of those makes sense for your particular course and your particular objectives.
All right, great. We do have quite a few questions coming in now, so feel free to answer however many you're comfortable before you'd like to move on. The next question, can you also do calculation of XRD?
So the answer is yes. We don't have that within this tool. I think there are some other ones on NanoHub, but ultimately, so you only need the coordinates of the atoms and the lattice to do that. You don't necessarily need any DFT calculation. So it's sort of a slightly different sort of task, but I think there are some things elsewhere on NanoHub that can do that.
All right, great. The next question, can quantum espresso calculate Raman spectra of molecules only having no periodicity or unit cell?
So yeah, absolutely. I mean, quantum espresso is, in general, maybe best suited to doing calculations of something that's periodic in some direction. But if we just put some empty space around it, you're basically calculating like a fake crystal where there's just kind of a big box and the molecule is in the middle. And you can certainly do Raman spectra for that too.
So I see one last question in chat. Do you have a tool to build up surfaces, nanotubes, and so on?
So I think there are some other tools on NanoHub that one can find for that. We don't have that quite within here, but you can use some other tools to build a structure, and then you can import it into our tools if one wants. Yeah, I guess I see in the chat also there was a question about automating the calculations. So when one could try to automate them, that actually sort of defeats the purpose a little bit of the cure. So the idea is actually the student is doing the automation and doing some of the checking, but one certainly could think of how to do that. And there was a question about the parallel things. So NanoHub has some clusters that are at Purdue and maybe some other places where the calculations can run. So that's what's going on the back end, which is nice. Okay, good. As it's 9:30, I think this is a good time to pivot to doing the hands-on calculations. We can see some more questions later as needed. Here's the MIT Atomic-Scale Modeling Toolkit, and so we're going to launch the tool. And so here we have a bunch of different things in here, and so we're going to start with an exercise that is about understanding covalent ionic and van der Waals bonding in diatomic molecules. So for this, we're going to select quantum chemistry parenthesis games. So this is a tool that allows us to just do some molecules. And next, what we're going to do is we're going to enter some coordinates. So we're going to start with the hydrogen molecule. So I'm going to go to new, and I'm going to put in a number of atoms and coordinates for one hydrogen atom and coordinates for another hydrogen atom. So these are located at -1 angstrom and 1 angstrom, so we have a bond length of 2 angstroms. This is too big, but we'll find out what the correct one is supposed to be. So we're going to set just a couple of other options here, like this is a basis set. This is a very small molecule, so we can just do something fancy here. We're going to do DFT with the B3 lip exchange correlation. functional, and we're going to go to optimize structure and go. So this is going to figure out for us what is the optimum bond length. So it's going to write up a bunch of stuff here. Boom. So it popped up open JMOL for us here. So that's our molecule. We can look at a few things here. So we have key outputs. I'm going to start by looking at atomic coordinates. So these are what we've gotten through all of the coordinates. And the last one, that's the relaxed structure. So you can see it change from 1 to 0.372. So 2 times that, or 0.74. That's angstroms. That's our optimum bond length. We can also, so I'm going to start by I'm going to type that in here. 3723. And so we're going to do a new calculation, which is actually at that optimized one. We can also look in here and see, what's the energy supposed to be of this one. And so it's minus 1.17 Hartrees or minus 31.9 EVs. That's our bonding energy here. So after we've optimized it, now we can go to just energy only. I put in the coordinates that we've gotten for the relaxation. And we are going to run it again. And what we're going to do is we're going to look actually at molecular orbitals in this case. So there's our molecule again, so it looks about the same. So we're going to focus now on the eigenvalues. So this is telling us what the energies are. And so you can see nicely listed. Here's our HOMO, minus 11.7 EV, and our LUMO. So this is highest occupied molecular orbital and lowest unoccupied molecular orbital at 1.6 EV. So something that's useful to know is we're going to try to make a table of this and some plots. And so you can actually go here on this little green arrow thing and go to data as comma separated values and get this data here. And so you can actually select this and cut and paste out of it, which you can't do otherwise without using this little gadget. So that's nice for putting this into a spreadsheet or a data file or something. So let's actually try to visualize our molecular orbitals. So this is something that's kind of cool. This tells us something about the bonding. So we're going to right-click in the window, and we can go to surfaces and molecular orbitals. And then these are in energy. These are actually in Rydbergs here. And so the lowest one, this is our HOMO, and the second one, that's our LUMO. And so we can actually look at each of these. So let's start with the HOMO. So we get this blue surface here. We kind of can't quite see it here, so I'm going to go back to menu, zoom, and 50%, and now we can see things a little bit better. So that's our highest occupied orbital. It just is shown in blue, so that means it all has the same sign. And this kind of shape, this is classic shape we'd expect to see for a bonding orbital. And you can get this from a nice, simple model that we talked about in the book, which is in our textbook, which is the Huckel model, or which is the molecular version of tight binding that we talked about later in the course too. So that's nice, showing us covalent bonding. What about the LUMO, the second molecular orbital? Let's have a look at that. There we go. So now we see that this thing, well, it's kind of farther away, but most importantly, it has a node in the middle where it's 0, and it changes sign from blue to red. Right, I'm seeing a question. What's the textbook we use? So the textbook we used is Oxford Solid State Basics by Simon. Which I thought was quite a nice book for this. Do I have it lying around? No, but that's what we used. So anyway, so here's our LUMO, and so this matches very nicely what we expect from that model. So we can see, what our bonding orbitals look like. So that's nice. The next thing that we worked on in the discussion is that we're actually going to look at, as a function of bond length, this energy and also the HOMO and LUMO energies. And so the way that we do this is you can just in here just take these numbers. These are half the bond length, and so you can just put in a few numbers both higher and lower than this. You can capture these eigenvalues. You can capture the total energy out of here, and then you can make some plots and try to think about that of what does it mean. So that's going to be a little bit time consuming. So I'm just going to show you some example outputs from that. Here are two plots that I made. So the one on the left is the total energy, which well, I should have labeled a little bit better, but so this has the classic example that we've got a minimum here. It goes steeply up on the left, not so steeply on the right. It's just what you get from some simple models. And then on the right, this is the HOMO and LUMO eigenvalues. And so again, just as you can see from the Huckel model, the bonding orbitals like HOMO, this goes up in energy when you stretch it, whereas the LUMO goes down in energy as you stretch it, and the two are coming together. And so this matches very nicely with our simple model of covalent bonding and helps us to understand how that's working. Well, for condensed matter physics, we don't necessarily care per se about the H2 molecule, but exactly the same thing happens in solids as well. So it's a nice simple version to look at. We went on from there to look at some other molecules. So we can look at ionic bonding with lithium fluoride, and we could also look at van der Waals interactions with helium-2. So I'll just show you quickly the lithium fluoride case, which I think is relatively straightforward and interesting to understand. So, okay, so for lithium fluoride, we're going to go now. This actually appears in our list here as an example. And so we could do this relaxation as well. It turns out this 0.8 is pretty close to where you're going to get anyway with these parameters and to the real value. So we don't necessarily need to do that relaxation. We can just go ahead and calculate based on that. So let's try it out. This one has a few more electrons, but still is pretty quick. And so here's our molecule. So now we have two different colors. One piece of info that's good to know in our interpretation is lithium is purple and green is fluorine, based on just the default colors in JMOL. So let's take a look at our molecular orbitals. Let's go to our eigenvalue log. So this is showing us what's occupied here. And so we can count up. So there's a bunch of occupied states, not just one like before. Number 6 we can see is the highest. Okay, it's actually degenerate with number 5. And number 7 is the LUMO, the lowest unoccupied state. So we're going to look at orbitals 6 and 7. You can also see that in this view here. So coming back over here, can go to our molecular orbitals. It's much longer list now, so there's more electrons. So let's take a look at number 6. And so look at that. So this is interesting. This looks kind of like a p orbital rather than an s orbital like we had before. But most importantly, in terms of the bonding, we can see this orbital is only on the fluorine. It's not. I mean, there is a tiny bit that we don't see on the lithium, but it's really on one side of the molecule, and that's the signature of ionic bonding rather than covalent that we can see. And let's have a look at the next one. So number 7, and look, that one's on the other side, and so that's again exactly what we expect from the simple model of ionic bonding, and so we should see that the orbitals are basically on one side or the other rather than being shared together as in covalent bonding. So that's a nice application. If you look at this with helium, essentially what you see is unmodified orbitals. They just kind of don't care about the presence of one another, and that's the classic sign of van der Waals bonding. Any questions about this? About these examples of looking at bonding in here?
I saw one question come in for how many numbers of atoms can we use with this tool?
Yeah, that's a good question. It depends somewhat on the parameters. So I would say in games, I mean, we have examples that are up to I think up to 20 atoms in here, and those are definitely ones that work, right? So these ones are 20. It's going to take a bit longer, certainly, but you can do it. In for quantum espresso, so the runs that we did for the cure are 3 atoms in the unit cell times 16. So we had, right, we had, no, times 4 rather. Yeah, so we had 12 atoms in the unit cell, I think. And you can definitely do substantially larger than that for just DFT. When you try to do the phonon calculations, that gets a lot heavier. Um, So yeah, these are all things that work. I'll show you in a moment, like this is a quantum calculation that we're doing. If we do classical calculations, you can easily do hundreds of atoms. I'll show you an example of that um, in a moment.
All right. I also saw another question. Can we do this with polymer materials?
Yeah, absolutely. Um, in games, I'm not sure if we can do periodic systems. So I mean, you could certainly do like a monomer of the polymer, or you could do an oligomer where you have, three, say, pieces of it together. In quantum espresso, you can do a 1D chain, and so that can be a way of modeling a polymer material. So yeah, these can all certainly be done. Cool. So let's move on to now another example application. So this was about bonding that we looked at in the beginning of the course. Um, so yeah, actually, there's also Siesta, so another DFT one. We didn't use it in the course this time, but I have used it before. So you can do some stuff like that here. But what I want to look at now is this one, molecular dynamics, carbon nanostructures, and more. So here we're going to do some classical calculations. Um, Oh, sorry. Actually, I mean the other one first. We're going to look at molecular dynamics, Leonard Jones. So this is something where you can explore just the idea of structure of a crystal or a solid versus a liquid. Um, what we're going to do here is we're going to look at some atoms that are interacting according to this classical Leonard Jones potential. It basically tells us something about repulsion and van der Waals interactions. So we can start with just the defaults here, which will show us something. And this is basically telling us something like some argon atoms, for example. And it's going to give us this little video of what happens. So it starts as a crystal, but then they just start to move around. And this is from thermal energy. And this basically becomes a liquid or a gas afterwards. So the temperature that we're working with is above the melting, so it just sort of immediately melted because of the temperature here. So we can have a look at this thing, the radial distribution function. So this is also known as G of R, or the pair distribution function. And this is something we can use to try to understand the nature of a set of atoms. And so what this tells us is that there's some kind of distance between atoms at which they just aren't found, and that's because they have repulsion from one another. But then there's a particular distance at which they're very likely to be found, and then there's some kind of a dip after that. And so a shape like this is classic for a liquid, essentially. That was a pretty coarse calculation. We can do one that is a little bit more detailed here. So I'm going to set a larger number. We're going to set our temperature to 0. They are going to end up having temperature, but that's just initialization. We're going to try a bigger box, longer time step to get things going. We're actually going to try more simulation steps. We're going to turn off JMOL because it doesn't really play nicely with such a long run. And see what we get here. So this kind of give us a bit more data to work with. There was a question about some good resources for understanding different DFT parameters. If you look at some of the other supporting documents that are in this tool that are from the Berkeley class, you can actually see some discussion of that. So that's one place I would suggest. So this code is running a real standard research code called LAMPS under the hood. You'll see some comments about that in here. So this just finished, and let's look at our radial distribution function now. So as we have a lot more data, we see something now which is smoother. It also extends out to a longer distance. And so again, this is pretty classic for a liquid. So there's kind of nothing here. There's a big peak. Then we have some oscillations at different distances. So this is kind of a first nearest neighbor, second nearest neighbor, third nearest neighbor, etc. Santiago is asking, how do we compare with real experimental data? So this is something that can be compared directly to X-ray or neutron scattering. So you can find a lot of literature about things like that. And so finally, we'll just try one other tweak here. So I'm going to go down to 10 simulation steps only. So it's very small. We're going to turn back on JMOL and try this out. And in this case, so now we can see better what was going on here. So that was this initial lattice, and you see that they just kind of move a little bit out of their positions. And if we go to our radial distribution function now, so now we're seeing something that's just characteristic of the crystal that there was at the beginning. And so you can see the pair distribution function now is just these individual spikes. And so that's what we expect to see for a solid. In a solid, there are just certain distances at which the atoms can be found from one another that are related to the lattice constant and different bond lengths. And that's what we have here. When we let it go longer, it melts and it becomes a liquid. And yeah, now we're going to go to something a little bit different. We're going to actually look at graphene here. And so the other molecular dynamics tool we have here called carbon nanostructures and more. We're going to set dynamics, thermostat. We're going to look what happens as a function of temperature. We're going to go to graphene in here. So you can see these are some quite large structures we're working with here. As these are classical calculations that are much faster. We're going to go to some longer number of simulation steps, and yeah, rest looks good. So let's fire it up and see. This is at 300 Kelvin. So we're going to see what happens here. See some stuff running, it's analyzing the data, and here comes our JMOL view. And so it's hard to see much in this view. We can kind of turn it around. So that's the structure we're working with, and you see some stuff is moving around a little bit. That's what happens just at 300 Kelvin here. Let's see what this looks like in terms of the radial distribution function. So here we see something kind of like what we had before for a crystal. So there are just certain distances at which we find the atoms located. Let's see what happens when we crank up the temperature now from 300 Kelvin. So, okay, I had listed 600 as an example. Let's go higher. Let's try 1200. See some slightly more dramatic effects here. What's going to happen? And so here you can see that there's some slightly more dramatic things. Stuff is moving around, all right, at 1200 Kelvin. And something actually kind of interesting is happening here. So the whole structure actually starts to distort. This is one of the characteristics of 2D materials, which I had mentioned in the lectures for class 2. It's related to this thing called the Mermin-Wagner theorem, but basically it's very easy for 2D structures to distort out of plane and do this kind of thing. And this is something that is experimentally observed. So let's go and look at our radial distribution function. Whoops, not that one. And so, now we can use this feature in NanoHub where we can compare two data sets together. So this is at 300 Kelvin. This is at 1200 Kelvin. So we can see the peaks have actually come down and they've spread out. And so that's, just a nice illustration of the main thing that happens to the radial distribution function. Things spread out because there's not just one single structure at high temperature because the atoms are oscillating around their positions. We could see this even more dramatically at 2400 Kelvin too, where the material actually starts to really contort in that case, which is kind of cool to see. So you know what? Yeah, let's just put that into and then fire that up, and then finally we'll go to the looking at an espresso calculation for a moment. Some other questions come in here. So Ming Chi says, we got some value for R equals 0. Yeah, that's actually, I was noticing that it's a good eye. That's a bit weird. I think maybe two atoms are accidentally on top of each other in the way things were set up in the argon Leonard Jones one. That certainly is kind of unphysical. So, that's an interesting and curious thing that can happen. You see how much things are bending here. Ahmed is saying the effect that of this bending. This is related to the Mermin-Wagner theorem. I mean, which says basically that you have instabilities in a 2D material. That also applies to kind of magnetic order and other things like that. Yeah, and there's all kind of rippling effects that people have seen in 2D materials, which are interesting, right? And so you can see it's very dramatic what's happening at 2400 Kelvin. We go back to our radial distribution function here, right? That's what we're seeing now at 2400. That things are yet lower and wider peaks. The resolution is maybe not quite enough to see it here, but you can also try to see some effects of thermal expansion that will happen too within these structures. It's a topic we also talked about in class. Okay, and now finally, I'd like to go to one of these quantum espresso calculations. So this took, I think, at least 30 minutes. I didn't pay close attention. Too long to run in here. But so you can see, these are some of the settings that I put in here. This actually ran the phonon calculation. We had some different things set up here. In the handout, I have the parameters that were used here. But so this is molybdenum disulfide in a monolayer. We do SCF, we do phonons, and we can actually visualize the results we've got in XCrysTen here. So that's our structure. If we want to see the phonons, we can go to forces. And so now we get these arrows that point in different directions. Let's kind of straighten this out a bit. So we can see this is an acoustic mode, so they're all going in the same direction. In this panel here, we can look through 9 different modes. So, how about that one? So this is, the two sulfur atoms are going in different directions. Another mode here. Now the sulfur atoms are moving and the molybdenum atom is going in the opposite direction. We can look at some out-of-plane modes like this. And so we can look through all the different phonon modes of this structure. That's the kind of thing that we did for the class exercise with these more complicated alloys. I think this will show us, the stuff again. Good. We also have some kind of output summary here, and maybe most interesting is here. That's the Raman spectrum. So there's kind of one big mode. There's also a couple of, or there's also a smaller one here that we see in our calculation. And these, we also have a bunch of kind of raw files if you wanted to look at these in something else. If you want to see more about how to do some details in quantum espresso, I invite you to sign up for the webinar that Dr. Enrique Guerrero is going to do next week. He's on the line with us here too. It's been answering some questions here helpfully, so you can get some more insight from him on how we can do some cool calculations for condensed matter physics and quantum espresso. yeah, I'd like to thank you for your attention here. Yeah, we can look at another couple of questions. Can we create a job file for heavy calculation from the toolkit? Says Ahmed. So the way that this works, again, we should try to avoid needing to actually understand this stuff well. It's in the calculation parameters. So you can go to run in parallel, and it's going to make you a job script. You can set how many cores you have, how much time you're willing to wait. Essentially, these are the two things that are used for the job script. It's going to set that up for you on the back end to submit this to a cluster from NanoHub and give you back results. So it depends how many other people are trying to use things about whether this runs promptly or not. What textbook? I think I said this before, but maybe you didn't hear it. So we use Oxford Solid State Basics by Simon, which I think students were pretty happy with. Okay, cool. Question from Santiago about a paper that I'm most proud of. That's an interesting one. I mean, yeah, I'm not sure I go exactly with the one I'm most proud of right now, but I mean, certainly I like the paper that just came out today, which was an experiment in theory collaboration, where Enrique is the second author on that one, where we looked at figuring out about structure and mechanism for trends in friction for rhenium doped MOS2. So that's kind of a cool one that was in nanotechnology. Can we do heavy molecules with gold in here? Says Ali. So I think so. There's actually some quantum espresso. Yes, in games, there's some funny issue about the way basis sets are set up for heavy elements that I didn't quite figure out yet in games. So you can run into a few issues in there. Chandrasekhar, it's a good name for a physicist. Excellent. Looks like asking about modeling substitution doped graphene. So you could certainly do that in quantum espresso here. That's kind of similar to the MOS2 alloys that we were looking at in the project here. That's definitely possible.
All right, I see a question that just came in Q&A. What are the largest reasonable simulations that can be done with AB Initio MD? How important is this limitation for research?
Yeah, that's a great question. So, I mean, for the most part, it depends how big a supercomputer you have access to, and how much time they let you do on it. So, I mean, this keeps advancing as they make bigger and bigger ones. I think there definitely are ones out there with certainly with hundreds of thousands of atoms, and the how long a time you can run it for is also really important for what kind of information you can get out of ab initio MD. And I think microseconds, I think has been done. I mean, there's some truly huge ones that people have been doing. So obviously, you're not going to get anywhere close to that within NanoHub. We don't even have the ab initio MD per se. I mean, you can do that with quantum espresso tools, but we don't have that. We don't have that implemented in here. You can do classical MD. You can do much larger than ab initio ones. And the numbers I'm quoting just multiply by a factor of 1,000 to 1,000,000 for what you can get to with classical rather than quantum ones. In terms of limitation for research, kind of depends what you want. I mean, people ambition just keeps on expanding as computer power grows. So people are trying to look at something like, for example, crack propagation, I think is a classic example of something that requires millions of atoms to just even make anything sensible out of it. And so people have been doing, more realistic, more complicated simulations of that over time. Let's see, Haying us, can I comment on Monte Carlo simulations? So, I mean, so we have 3 different flavors of Monte Carlo you can do here. So, hard sphere Monte Carlo. This is actually literally the original Monte Carlo calculation. A paper from it's like 1952 or something about this. So this is basically studying solid to liquid transitions. It's kind of similar to the Leonard Jones one that I showed you. You can do Ising model Monte Carlo. So this is for studying magnetism. So you can look at magnetic phase transitions here. And then finally, this one is a bit more sophisticated. I have not used this in my class that you can. You can actually do quantum Monte Carlo here. These are much more complicated and heavy calculations than DFT, but in general are more accurate. We actually had done a study within for the computational nanoscience class. You can look at the dipole moment of carbon monoxide, which is surprisingly difficult to get correctly, and look at how well quantum Monte Carlo does on that. But yeah, that's I think a kind of advanced topic. Hello Connor. So is this can this be used as a teaching resource by anyone, and is the backend freely available for running the example? So yeah, absolutely. We're not using any special permissions even for doing this on the class. You can just log in. You can just run all of these things and do it in the same way that the students did in my class, and use it for your own classes and stuff like that. So as long as you get the account, that's the only way that this is regulated.
I see another question that came into the host privately. Can we model molecular dynamics based on drift diffusion transport balance due to electric field at the same time?
In general, sure. Not within this tool. So I would say, we're not really focused so much on some fancy stuff about MD within this tool. You can definitely find some other ones that do some more sophisticated stuff for MD, with something like what you're describing, and some other tools on NanoHub. I think there's like the Poisson-Boltzmann method. I think there's at least one tool I had looked at once that does that. I think that's something kind of along the lines of what you're thinking about. I mean, the most advanced thing I would say that we can do for molecular dynamics here is you can yeah, I think it's in this one. You can actually calculate a diffusion coefficient. I mean, diffusion is not part of the model; it's rather a thing that you're calculating ultimately. So you can calculate that for liquids, for example, which is something nice.
Well, looks like one more did pop into chat here related to siesta. Trans siesta might be what you would need for directly combining DFT and MD. Also look at EPW as part of quantum espresso. Oh, thanks, Tim.
Oh. Yeah, EPW certainly is good for that. Somebody asked about electron phonon. I thought the trans siesta actually does transport rather than MD, although maybe they have some other stuff that I'm not thinking of in there. I mean, within quantum espresso, there's the CP code that does MD. There are several options for how one can do ab initio MD. I think there may be some other tools that do that. In general, there's some pretty big calculations, so they're kind of hard to do some really meaningful examples. So that's why we focused on classical MD within this particular tool, which is much more useful, I would say, for a pedagogical perspective. But certainly, ab initio MD with DFT has its place.
All right, great. I think that is the end of the questions that have come in. Thank you very much, Dr. Strubbe, for this wonderful presentation today. And thank you to all of our panelists who are answering questions today, Dr. Guerrero and Dr. Fultons, and to all of our attendees. Thank you so much for joining us, and everyone have a great day.
Great, thanks everybody for joining, and happy simulations. Hope that you can do some cool things and set up cool things with students with these tools. And thanks to the NanoHub folks for the opportunity to do this.